All right, good afternoon, everybody. I think we'll go ahead and get started. So, welcome to today's webinar, all about toll plazas. For just a little bit of logistics here, so we do have a live audience here in the crowd, and welcome to the folks that are here in the room, as well as those that are joining us remotely from all over the world. So we've got what I think is a pretty interesting series of experiments and projects that tie together in and around some of the work that we've been doing across our UTC consortium with respect to toll plazas. And today the plan is to highlight a flavor of some of those experiments, both to talk about the results that relate to the toll plaza environment, which we all know is a tricky situation to design and operate and manage on our roadways and is an area of safety concerns, but also to showcase the power of driving simulator technology as a tool for evaluating different toll plaza scenarios. So my name is Michael Knodler. Yeah, you're hearing me in stereo. That's tough. I'll stand back, maybe. Is this a little better? All right. Yep. Jacob's going to test it out in the other. Jacob, is this working? Test, test, test. He's going to see on the webinar. but thank you for the confirmation. All right, so I'll go ahead and keep going here, and we'll await confirmation that everything is working. As I started to say, my name is Mike Knodler. I'm an associate professor at the University of Massachusetts-Amherst. Joining me today as part of the webinar is Dr. Mohamed Abdel-Aty from the University of Central Florida, and Dr. Didier Valdes from the University of Puerto Rico-Mayaguez. And they're going to be coming up to the podium in just a bit to talk about some of the work that's happened here. So first, a little bit about SaferSim. It is our UTC safety research using simulation, or SaferSim. There's 5 member consortiums led by the University of Iowa, which is where we're actually at today. We're in the old Iowa Capitol building, which is a really remarkable facility. So thanks for the hospitality, as well as our colleagues at the University of Wisconsin, and then the 3 universities that are represented as part of the webinar, UMass-Amherst, University of Central Florida, and University of Puerto Rico-Mayaguez. And the highlight of this particular consortium is the use of both microsimulation and driving simulator technology to study aspects of transportation safety. And one project that we've started from the beginning, which actually folded into a series of projects, is in and around the toll plaza environment. And as I mentioned earlier, and as you'll hear a little bit more some of the statistics as we get into it, the toll plaza environment is one of the more challenging scenarios. At the University of Massachusetts, we replicated one of our more challenging toll plazas. One of our graduate students, Farouk, who's in the back of the room here, built and constructed a toll plaza to scale exactly as it was out in the field and studied several different things. Within this particular consortium, you'll hear a little bit more about an experiment that we ran both in Massachusetts and in Puerto Rico on the exact same scenarios to study the effects of driver familiarity with particular signage. You'll also hear today about traditional toll plazas, dynamic tolling, the hybrid toll plaza, which was evaluated at the University of Central Florida. And we'll talk a little bit about applications in open road tolling, and then talk a little bit as well about the potential for toll plaza signage and design in and around managed lanes. So the plan today is to talk about 2 of the experiments that were done in a bit more detail. And so we'll start first with the hybrid toll plaza that was evaluated in Florida, and then we'll transition to the scenarios that were evaluated in the University of Puerto Rico. So with that, please let me go ahead and bring up Dr. Mohamed Abdel-Aty.
Thank you, Mike. All right, good morning. My name is Mohamed Abdel-Aty. I'm the Civil Engineering Department Chair and a Professor of Transportation Engineering at the University of Central Florida. And if you're not very sure where the University of Central Florida, it's in Central Florida, in Orlando. And it's the 2nd largest university in the country with 65,000 students. As Mike mentioned, we are looking at Toll Plaza, and this was actually a key project from the beginning of our UTC. Of course, we have identified very early on the significance of tolling and road pricing, since we all know now and understand that there is a problem in funding our highways, and therefore, with limited revenues from the gas taxes, we have to find innovative ways, and Florida has been in the forefront for a long time with tolling, and now with managed lanes and dynamic tolling, etc. So I think it's starting to get more and more accepted around the state of Florida, and soon it will be also around the country as a way to fund transportation. This is an example of one of the toll plazas in what we call the East-West Expressway, or State Road 408 in Orlando. And this is what we call a hybrid toll plaza, because it combines the open tolling as well as the traditional exact coin and cash type tolling, as you can see from the picture on the right. Now, with a lot of different tolling systems in different states, and for a while there was no standards, and particularly Florida has a lot of tourists and visitors also, there are a lot of confusion about toll plazas, and particularly, changing the design also makes a lot of people unfamiliar and confused. So we thought there is an important safety impact, and we have been studying actually crashes at and around toll plazas since the 90s, since we had the traditional toll plazas, and we have several early publications in this particular field. And before we designed the experiment, actually, just wanted to show you one of my students driving the simulation through the toll plaza, but this is really not very important now. So we have identified, before we actually designed our experiment, we have looked into crash statistics around the toll plaza area, and we have, from the crash history, identified the problems and the locations and the type of crashes and the severity of crashes. So really, the design of the experiment came based on a lot of knowledge and a lot of background work. But we ended up with, you can see here the plaza in the middle of this picture, and then there are up and downstream locations. And we have also collected traffic information from Wavetronics microwave detectors at these locations to get actually the speed profiles, the volumes, etc. In the field, which we will feed into the simulator, as well as we will use to validate the speed distributions in the simulator. So this is one of the things also that we did. We have identified 4 main critical zones to study, which, of course, zone number 3 is the toll plaza area, which has a combination of open tolling as well as the manual and the cash, but also the area upstream and downstream, which happen to have, in our particular plaza, an on-ramp and an off-ramp. So it complicates even, and this particular plaza is very interesting from a design point of view, because it has an on-ramp upstream and an off-ramp downstream, and there are a lot of weaving for people entering or exiting and needing to go to the through lanes. So it makes it a little bit more interesting to study. Going to the simulation, the driving simulation experimental design, we recruited 72 subjects. We obtained IRB approvals, of course. We had 24 different scenarios, which I'm going to elaborate on in a minute. And we ended up that every participant had to, or were assigned randomly 3 of the scenarios. And also we had a questionnaire for the participants to obtain information. Now, with respect to the subjects, we also made sure that the recruited subjects represent the population of Central Florida. And we had, not in Central Florida, but users of this particular expressway. And we did it using what's called the quasi-induced exposure method, If you are familiar with safety analysis, you might be familiar with this method, which is basically consider the innocent driver in two vehicle crashes as a random population of the expressway. So the guilty driver or the driver that was cited always could be biased, right? Because maybe younger or whatever, but the innocent driver is usually random. So if you look at all crashes over the roadway and they look at the innocent drivers, this represents a random sample of the users. So you can see here the comparison of the not at fault or the innocent drivers as well as the drivers from the subjects that we recruited, and you can see that the distributions of age and gender is to a large extent similar, and of course, we did chi-square, etc. So we were comfortable with the sample that we used, that it represents our population. So what specifically did we look into? We looked into the different paths, because there is different ways of entering to the plaza, and I'm going to elaborate on a minute. The signage, the pavement marking, the traffic conditions, congestion or peak, off-peak, etc. And we got these values, of course, from the detectors that we have in the field. And also, if we change the distances up and downstream to the on-ramp and off-ramp, because as I told you, it's a little bit tight, this plaza design. So these are the different paths shown in different colors, and the description in the table indicate, which is basically, I don't want to, I want to give the time to my colleague also to talk about the other experiment, but you can see the path. Basically, people are entering from ramps, exiting off ramps, some of them going through, some of them going and paying cash, etc. And you can notice at the area upstream and downstream, there is weaving, and this is a concern, of course, that need to be handled with messages, with the information signage, and also with the pavement marking. Just to give you an idea about some of the scenarios, and I'm not going to go over every single scenario because we have 24, as I mentioned, but here is the existing condition with respect to the signage upstream of the plaza. There is another one, which is sign number 1, which is way upstream, so it's not really influencing our experiment here, but you can see that immediately downstream of the on-ramp, there is a sign, and then immediately before the diverge between the through lanes and the plaza lanes, there is another sign. So this is the base case. And then this is one of the scenarios, and this is again based on analysis that we did before we entered into the experiment, is actually to move sign number 2 to the new position upstream of the on-ramp, and then add a portable DMS on the ramp, asking people to, or asking drivers to remain right, even if they want to go to the through lanes, because this would cause a lot of disturbance and weaving if they want to go to the open tolling lane. And still their ETC system work through the existing structure of manual lanes. So they need to keep right rather than trying to merge, which is causing, as we saw, a lot of problems in the crash statistics, like angle and side swipe type collisions. So this is a suggestion that we had. Also get rid of sign number 3 and just use sign number 2. Sign number 3, in our view, was a little bit confusing and late for people. Even that want to use it, it's too late to use it. And it created confusion that we saw in the crash statistics. So that's why we wanted to try getting rid of it. With respect to the marking, here is a picture from the field as well as the scenario itself. You can see we are helping drivers that want to pay cash to keep to the right rather than merging from the left, the most left lane suddenly to pay. So we are kind of helping them with marking to keep right. And the base case is basically having no marking at all. And this is actually new. I mean, very seldom you find for toll plazas marking that is helping drivers. Usually you have signs, but not marking. These are some of the information that we got from the questionnaires. Education, age, gender, income, the regular variables, but we also looked at whether the driver is professional, and professional means a professional driver versus a regular, commuter. We looked at crash experience, if the driver was was involved before in crashes, or at least one crash. We looked at whether the driver is actually having the electronic system or not in his, actual driving. We looked because again, Orlando is a location where we have a lot of international drivers, really mixed population. So we also wanted to look into this factor, whether the familiarity, whether you are really from the area and familiar with using these plazas, or you are a new driver in the area. So actually, we did also look at that. Quickly, these are some of the factors and their levels from the questionnaire. And I think I'm going to go quickly here. With respect to driver behavior that we collected from the experiment, we did collect about 7 different parameters that we thought represent driver behavior, as well as risk, or high level of risk. We here are showing 4 of them, which is basically how the speed profile changes based on the different scenarios at different zones. Also the standard deviation of speed, of course, that, in safety, we consider the turbulence in speed as an indicator of risky driving, or it has been proven to be related actually to high crash rates. Standard deviation of lane deviation, and also acceleration noise, which is basically standard deviation of the acceleration at different zones. The validation, as I mentioned before, we looked at the speed distribution at the different zones and in different locations, and we compared it from based on the field data as well as the simulator data, and again statistical tests, and the distribution, as you can see, shows that the experiment was valid. I mean, people basically drove as they drove in reality, which is one measure of validating our experiment. With respect to analysis, how we did analyze the data, we used multivariate linear models with random effects. And why did we do that? Because, as I mentioned at the beginning, every driver had 3 scenarios. So there we have, within subject factors. And in order to account for that, we use the random effects. And this is shown in the theta at the end of this equation. And here are some of the results, which I don't intend to go over in detail because I'm going to summarize at the end the findings. You can see that for average speed, we estimated 4 models at every zone. So we are looking at every zone because we thought that there is a difference in behavior at every zone, upstream, downstream, merging, plaza, etc. So we wanted to actually look at the behavior at every zone. So for every factor, I said we had 7 factors that we analyzed, multiplied by 4 because we have 4 zones. So here, for example, modeling the average speed at the 4 zones, and here are the significant factors, and you can see the specific path. Remember, we had 5 paths. The traffic conditions, the pavement marking, whether we can or not extend the distance to the on-ramp or off-ramp, from the on-ramp or to the off-ramp. Whether the driver is familiar, and we got this from the frequency of using this particular road, whether the driver is used to having ETC system, the education level, the income level, and whether the driver is new to the area or not. So these are the factors, but I'm going to explain to you in detail the most important findings in a minute. Similarly, the log of the standard deviation as a turbulence of speed factor, same idea. Standard deviation of lane deviation, etc. You got the idea. So all the same modeling methods for locations, different factors. And here are the significant results, the bottom line. I hope I'm doing well on time. Okay, great. So we of course, this is a non-brainer. The main conclusion, we would love to have open tolling, right, without structures. So we are, of course, we are moving toward it actually, and there are a lot of plazas now in Florida where we don't have any. Once you reach a market penetration above 90%, you really need to remove the structure. This is the best. So this is clear also in our results. We found that drivers tend to drive with less deviation, less acceleration noise, less variation near the toll plaza if there are markings. So marking is a good thing because it reduces some of the turbulence or some of the factors that we thought are not desirable. We also found that adding a DMS message on the ramp itself is positive also because, again, as I mentioned, it reduces the weaving of drivers coming from the on-ramp and trying to go to the through lanes. So our assumptions of the different marking and different signing strategy really showed in the experiment that these are good to be implemented. We found, as I mentioned also, that the third sign right before the diverge area is useless, even confusing. So we just need to remove it altogether. We find, of course, also that the distance, if we have more distance up and downstream of the plaza, it makes the driver more comfortable and gradually change. And this plaza is, honestly, I don't know, and I need to convey this to the Central Florida Authority, toll authority. Why did they put the plaza in this particular location with this particular tight design? I'm not sure. Probably they have reason, but the plaza could be shifted a little bit downstream or upstream. There is more room rather than putting it in the middle between an on and off ramp. Maybe they might consider just closing one of the ramps in the future if it becomes a problem. But I think they are moving to open tolling, so it might be obsolete soon, this particular comment. Of course, the congestion, we saw the congestion effect. We saw a certain driver effect, like the younger, older, and male drivers are risky. I mean, we know male and younger. I'm not sure about older. this is new. So maybe higher risk behavior with respect to standard deviation or turbulence. Maybe not high speed, but maybe the lane position, etc., are a problem. We also find that high education and high income and new drivers in the area and ETC users and people that don't drive frequently are more careful and they drive slower. I think it makes sense. And we found that professional drivers and risky drivers that have crash history have higher speed turbulence. So they are, they have a problem in this respect. So our main conclusion from these results, as I mentioned, we recommend, although the hybrid plazas are a good design and a good step after the traditional plazas, but maybe we need to go to open tolling. The recommendation of the DMS sign on the ramps, if there are ramps, is a good idea on ramp. We also have a specific recommendation with respect to the signage location and markings to the plaza. And I think this would be good information to toll authorities and USDOT. If I may very quickly talk about, before I hand the mic to the mic, M-I-C, not M-I-K-E, Michael, to Didier, is what we are doing right now. It is the next logic step, which is going now to what is very much desirable in Florida. It's already on a limited section of I-95 in South Florida. It's coming very soon to Central Florida I-4, and it's also coming very soon to West Central Florida in the Tampa area, which is basically taking a freeway and splitting it into free lanes and toll lanes at the same time. And this already exists in Texas, Virginia, in multiple locations as shown in this slide. So the idea, you want better level of service, you use the managed lanes, which is usually a couple of lanes in one direction. And these will usually have dynamic tolling based on the level of service. So if you want better level of service, you pay. And in rush hours, and you pay more. So this is the idea. If you want free service, okay, use the regular lanes, and you can, have delays. So this is basically, I think I think it's a good idea, and it's a good traffic management strategy also. So in Florida, it has been very successful, and it has been on I-95 for several years now. But it's only 14 miles. So it is it is very easy because it is one section. Once you enter, you cannot exit until the end of the section. So there is no drivers going in and out of the managed lanes as the toll change or as they change their mind or want to exit or whatever. So it makes it from a safety point of view pretty benign. Although we have looked at crash modification factors at 95, and we found that there is improvement, and this is very interesting result that we saw safety improvement in the managed lanes compared to before implementing the managed lanes, but we saw safety deterioration on the free lanes. So there is a mixed safety effect when implementing managed lanes. Anyway, so in a driving simulator, we want actually to represent this section of I-95, but we need to complicate it a little bit. So if it is longer and people need to get in and out the managed lanes, what should we do? There are some standards coming to us from Washington State and California. We don't believe they are enough, and we need to check them, and I think we need to change them. But there are no studies in this particular, it's just, good practice, but there is no really scientific study to see what we need to do when we have an extended managed lane. So we are actually, this is the design stage of the scenario, and with the help of NADS, we are now designing the new tiles that we are going to use in the simulator in order to test the lane changes and entering and exiting from a managed lane to the free and then out to the off ramps, etc. It's a little bit complex design, but I think it's going to become very, very important as we implement more and more managed lanes. So with this, I would turn it to my colleague Didier Valdes from Puerto Rico, and I thank you for your attention. I'll be very happy to answer questions at the end of the webinar.
Thank you very much, Dr. Abdel-Aty. All right. My name is Didier Valdes. I'm a professor at the University of Puerto Rico at Mayagüez. And the University of Puerto Rico is a minority serving institution and one of the 5 universities of the Safer SIM University Transportation Center. Thank you for the opportunity. I will be talking about the operational safety-based analysis of varied toll lane configurations using driving simulation. And as Dr. Knodler mentioned before, I will be talking about 2 of the research projects that we have undertaken at UPR to study safety and operational aspects of toll plazas. First, I will present a typical toll plaza through the study of the Caguas Sur toll plaza. And after that, I will present a dynamic toll lane facility and the safety issues associated with this type of system in Puerto Rico. So the general objective would be to apply simulation technologies to address these critical issues in transportation facilities, specifically related to safety. And considering the toll plaza configuration, the combination of cash and electronic toll collection lanes and managed lanes that we're going to see in the DTL study. And the scope, of course, is safety of all users in terms of operation, signage, and design of existing transportation infrastructure. The Caguas Sur toll plaza study, the Caguas Sur toll plaza is a 6 lanes toll plaza with a combination of electronic toll lanes and cash lanes. ETC is on the left 4 lanes, 2 for automobiles in the left and 2 for all types of vehicles in the center. And cash lanes are the 2 lanes on the right side with cashiers attending the toll booths for those drivers who do not own a transponder or would like to recharge their ETC accounts along the way. This type of toll plaza is typical in Puerto Rico and has been used also in other jurisdictions of the US. So this toll plaza has seen several changes over the years. Initially, it was an all cash lanes toll plaza with automatic gates and cash lanes. It was converted to 35 miles per hour speed limit ETC with cash lanes to the right. And afterwards, the left 2 lanes were expanded to allow 55 miles per hour higher speed ETC lanes Then the center lanes are 35 miles per hour speed limit, and the cash lanes to the right, where the vehicles must stop to handle the toll payment. This combination of possible speed, going back one. The combination of possible speeds is not well reflected in the signage that is used to alert the drivers on how to negotiate the toll plaza. Before the toll area, the speed limit is 65 miles per hour. However, approaching the plaza, there might be conflicting messages placed on the same section of the road because signs on the left may indicate 55 miles per hour that corresponds to the ETC, while signs on the right indicate a variation in speed limits from 55 to 45 to 35 as the vehicle approaches the cash lanes part and finally stop at the toll plaza. Therefore, in one section, a driver will see a 55 miles per hour speed on the left with a small supplementary plaque indicating ETC toll ahead, and a 35 miles per hour on the right on the same section. So it is confusing. So the idea of this part of the project then was to identify if that confusion exists and at the same time evaluate if an alternative configuration using overhead signage, including speed limits, would be better. Therefore, we created scenarios for these two configurations. Configuration 1 corresponds to roadside signage, which is the current signage used in the facility, and configuration 2 corresponds to overhead signage, an alternative that we have tested in this case, where the driver have information on both the type of lane that is available downstream at the ETC, at the plaza, ETC or cash lanes, and also the speed limit that should be observed according to the toll lane that they will use. That is what you see on the right of this slide. So we use our cockpit driving simulator at the University of Puerto Rico to test these configurations. The experiment included as independent variables the traffic conditions without traffic to all traffic, and the starting lane, starting at the right side of the freeway or at the left side, and the destination lane, ETC or cash. As dependent variables, we use the standard deviation of roadway position, SDRP, the average speed, and also the acceleration noise, which is the standard deviation of acceleration that has been demonstrated in the literature that can be used as a surrogate variable for crash frequency. So in terms of subject drivers, we had 20 participants, 9 females and 11 males, in a range of 18 to 70 years old to reflect the distribution of the driving population, all with valid driver licenses and at least a year of experience driving their vehicles. As you can see in the figure presented to the right of the screen, an schematic of the approaching zone to the toll plaza is presented for both configurations that were studied. Road signage, which is configuration 1, and overhead signage, configuration 2. The red object that you see represents a vehicle in one of the scenarios where the simulation starts on the left lane and should go through the cash lanes at the toll plaza. You can also see the 5 zones. Let's see, yeah, the 5 zones, zone 1, 2, 3, 4, and 5. The 5 zones that we use to collect data around the area where the signage is located. Now I'm going to show 4 slides presenting the type of graphics that we use to start our analysis, and after that, the results of the statistical analysis used to reach our conclusions in this study. This particular slide shows the trajectory of each of the drivers along that segment of the highway approaching the zone to the toll plaza in this scenario where the driver should pass through the cash lane. The blue lines represent trajectories for male drivers and the red represent female drivers. But what is interesting here is that one of the observations that we made using this graphic is the variability, and you can see that the variability is greater in configuration 1 than in configuration 2. Now, for scenario 11, another of the scenario, we had 12 scenarios for the various variables. So in another scenario, in this case, the subject started on the right lane and had to pass through the ETC lanes at the toll plaza. Again, we can see a greater variability in the trajectories associated to roadside signage than overhead signage. And this goes on. So, for example, if we would like to look at the average speed and compare the variations in average speed, we see a similar situation between both configurations in both the case where the subject should go through the cache lane or through the ETC lane, which is this other figure that I have here. So with that, let me go real quick to the findings. The results of the statistical analysis, considering the data of all our subjects and analyzing the dependent variables and making the Bonferroni corrections for the type 1 errors that may be induced for using data collected from the same subject, have allowed us to obtain the findings that are mentioned here. As you can see, there is also consistency in the results that indicate that for all the dependent variables considered, a standard deviation of roadway position, average speed, and acceleration noise, the overhead signage configuration performed better than the existing roadside signage configuration. Here you can see the specific zones where improvements will go from 8% to 50%. But the important issue here is that we have found that in terms of safety, having overhead signs to alert the drivers of the upcoming conditions at the toll plaza is safer. Furthermore, the dependent variable that we use as a surrogate, the crash frequency, which is acceleration noise, highlighted one particular result which is encouraging, that when we compare similar daytime and nighttime scenarios, acceleration noise for roadside signage is greater at night. Meanwhile, in the proposed overhead configuration, the variable is smaller at night. So it goes in different directions, which is excellent in terms of the potential for crash reduction, potential for improvement. I will risk to say just over 50%, but the number is greater than that. Okay, now let me talk a little bit about the other project, the dynamic toll lane study. Dynamic toll lane system along PR22 combines various congestion management strategies, including high occupancy toll lanes, reversible lanes, and congestion pricing. It is a combination of strategies that has been also implemented in various cities in the US. In Puerto Rico, it's operated as a public-private partnership. The PR22 dynamic toll lane and high occupancy toll system is a 2-lane reversible stretch. As you can see here in this cross-section, they're in the median of the expressway. Between the municipalities of Toa Baja and Bayamón, here in this map, you see the route that it takes. The PR22 is a 6 to 8 lane expressway, very congested during rush hours, that moves users from the suburban municipalities towards San Juan in the morning peak period and back to their homes during the evening peak period. Therefore, the HOT lanes operate as a reversible facility headed eastbound in the morning and westbound in the evening, making the HOT reversible system work as an infrastructure management strategy, adding capacity along the direction of heavy demand, entering or exiting the city of San Juan. It is referred to as an HOT lane, high occupancy toll, because It is a stretch of road shared by a BRT, a bus rapid transit system called Metro Urbano. This system has high-capacity buses every 15 minutes. So that allows enough free capacity to manage more than 1,500 automobiles per hour during rush hour, therefore reducing congestion along the main lanes of the expressway. The dynamic toll lane is an innovative congestion management strategy that charges tolls in a dynamic way depending on the congestion. So the toll increases from $1 to $4.75, and it depends on the, as I was saying, depending on the level of congestion of the expressway. Therefore, this is applied as a demand management strategy as well, that tends to spread the demand over a longer period of time, such that the user starts earlier to pay a lower toll. Now, let me talk about some problems here. There are several situations or issues that we would like to address, and we have started to address. The situations identified include the problems with the speed limits, an overpass column in the middle of the two-lane facility, reduced shoulders, and the entrances and exits of the DTL. So our initial work has concentrated in describing each one of these geometric and operational issues and addressing the speed limit situation. Let me explain this a little bit in more detail. The speed limit situation arises because there is a difference in speed limits between the DTL and the regular expressway lanes. Speed limit is set to 40 to 45 inside the DTL. It's lower than 55 miles per hour in the general expressway lanes. Therefore, imagine a driver paying a higher toll and traveling at a lower speed than the vehicles that are used in the general non-toll lanes. The drivers on this lane perceive that this is to mitigate congestion and significant delays associated with the high demand in the main lanes expressway. So they perceive that they have the right to go faster. Usually drivers go at the same speed in both systems. And after using this system for 5 years already, there has not been serious or fatal crashes reported inside the DTL system. If we have done some experiments with just looking at the speeds of the vehicles with a moving average vehicle, and the speeds are a lot higher than the posted speed limit. The main reasoning used to establish the 45 miles per hour speed limit in the DTL system was the lane width, which is 12 feet, and the shoulder width, which is just 1 foot. Then we know that they use the child line concept, to determine the speed limit, which is typical in this kind of designs. However, in practice, this two-lane DTL facility is not packed with high-speed vehicles. It has been operated to allow a maximum of 1,600 vehicles per hour for a two-lane facility, allowing enough space to operate at a higher speed. Furthermore, except for the BRT, only passenger cars are allowed in the DTL, and not semi-trailers or any other heavy vehicles. Therefore, this reduces the risk of exposure to the drivers as well. Now, regarding the other issues, the main problem presented was driver confusion at divergent areas. This problem is reflected in 2 places along the DTL. The first one is the section where a column that supports an overpass is located in the middle of the DTL. And it is very well shielded and delineated, but it can create a hazard and confusion to drivers at high speeds. And the second one is the incorrect use of the DTL entrances and exits, where drivers may expect to exit to the right of the system, but it is designed to exit to the left of the system because to the right goes the BRT. So that creates confusion. So we would like to study those 2 things. And as you can see in this slide, we use these zones of interest at the entrance, in the bridge, around the bridge, and the exit. This is going eastbound, but coming westbound, then the entrance is on the other side, of course, because it's reversible. Now we will have the entrance, the bridge, and the exit. Zone 1 is the general zone here. Zones 2 and 3 and 4 are in the middle where the bridge is, and zone 5, the entrance exit in the west part of the DTL. Now, in terms of the experiment conducted was to determine the speed selected by the users, if narrow lanes were used, and if and how the lane width affected their selected operating speed, okay? So in terms of independent variables, we consider the time of day, morning, evening, and night, the lane width, 10, 11, and 12 feet, and the posted speed limit. We vary all these three variables, and in terms of dependent variables, we use similar dependent variables in our previous study. In terms of the subjects, we had 27 participants, 14 females and 13 males, same age to reflect, same age range, 18 to 70 to reflect driving population, and experienced drivers as well. So let me show you a couple of our results. First, looking at the standard deviation of roadway position, you can see the trajectories that the subject drivers used. And going eastbound, you can see that some of the subject drivers try to exit to the left. The signage indicated that the exit was to the right. And coming westbound, similar situation happened. And the thing is that we observed that kind of behavior also in the field. So what happened is that creates a lot of confusion for the drivers, and if the bus is coming and trying to exit, it creates also a real hazard. Looking at the roadway position, zones 2 and 4 were the more critical ones identified in our statistical analysis. And these zones are around, in the diverging and confluence of around the column in the middle of the DTL. Now, we also studied the average speed and the acceleration noise. So you can see here the graphics that we got out of the results. And there were variations in both average speed and acceleration noise. And those variations represented a lot of confusion in the entrances and exits, and also the problem around the column in the bridge in the middle of the, oops, what happened here? All right. So the major research findings for this particular project, we just did the part of the variation in lane width. And so in terms of the standard position, we have the most significant differences in zones 2 and 4, as I was telling before. In terms of the average speed and the acceleration noise, we also found that there was a significant difference in terms of the lane width, and the final result was that the best situation would be to have the 55 miles per hour in the DTL with the 12 feet lanes. So there is still a need for further study, to go to the field and take some additional data. And we would like to develop some countermeasures and test countermeasures, including new signage configurations and pavement markings. And in the long term, we'll also evaluate maybe major changes that require changes in the infrastructure as well. I would like to thank my team, of course, at the University of Puerto Rico, Dr. Benjamin Colucci, and the students that have been working on this project, Jonathan Ruiz, Brian Ruiz, Ricardo Garcia, and Edith Colon, that have helped us to build all these scenarios and do the hard work. Thank you very much to you for listening to me, and going to Mike now.
Thank you, Didier, and thank you, everybody. So we actually have 3 more experiments that we could talk about, but once I saw that there were 57 slides in the first 2 experiments, we decided to table that one and save it for a sequel, and let folks read the research reports or reach out to us with respect to the other experiments that were carried out, again, including those across the different universities within the consortium. So we do have a couple of minutes left. Jacob, I don't know if there's any questions online that you want to moderate, or if there's any from the audience here, just so that we are capturing them on the webinar. I'll just run the microphones in your direction.
If you now widen the lanes in the DTL and you raise the speed limit, are you worried that, because right now, at least in the United States, or up, you know, wherever we are here, people always go higher than the speed limit. So are you worried at all that you're going to give them this sense of more space and the, you know, sense that they can go faster, and that they just might keep going faster than that, and that might increase your risk?
Well, in the experiments that we did, at least, since we were varying the speed limit also to 55 and 65, even with different lane widths, even for 55, people really, I think they felt the shy, maybe. I don't know what exactly, but they didn't go overboard with that speed limit. So they stayed lower than 65, but higher than 55. So, and for the 10 feet lane width, they didn't go over 55. So even though the speed limit said 65 miles per hour. So if we have reasonable drivers, I think that's the behavior.
Mohamed, one of the surprising results I found was that both professional drivers and older drivers were more risky in your experiment. And I wondered if you had any insights for why that might be.
Yes, what I didn't elaborate on is based on which factor, because we have 7 factors. And Montez, can you help me out with this? Which factor did we use in order to determine that professional drivers and international drivers have a higher risk? Which factor exactly? Yeah, this is not the question. Which factor? Is it the speed, the variance? How did
all
we
of
decide?
them. All of them. Like the speed, the standard deviation of lane deviation, and the acceleration rate and deceleration rate, all of them. So it's all of them gives us the same results.
I'm not sure all of them were significant in all the models and all the zones.
It's not all the zones, like it's depend on the zone.
And not all the models.
It's, yeah.
Okay, so professional drivers, maybe, I don't, I mean, honestly, I don't remember, but you know, it might have been like a specific variable, like
In here in
the variance in acceleration, I mean, they're more aggressive in acceleration, for example. You know, a particular factor that led us to believe that they are in certain locations, in certain situations are more aggressive. But on top of my head, as I told you, it's 24 models, so I don't know exactly which one led us to believe that. And so the professional and the other ones you mentioned was, yeah, the older drivers probably, they don't speed, so we're not talking about high speeds, for example. We're talking probably about either standard deviation of speed or lane deviation. So again, it's a little bit complex to map the 24 models with a specific factor. And so, but if you're very interested, I can share with you all the models and we can really dig where we concluded this. It is his thesis, that's why I referred to him, but he didn't help me out. So.
no, it's actually for the professional drivers, it's for the speed variation in the toll plaza zone, in the zone 3, third zone. That's the most one that gives the significant result.
All right, so we're just about out of time here, so I think we'll go ahead and wrap up the webinar and encourage anybody that is online to follow up with us regarding any questions that they may have. Feel free to reach out and let us know of those questions. Also, for those that are either here in the room or online, this will be posted online. So the webinar will be posted in the next few days, so you can go back and catch any parts that you missed, or if you just want to watch it again, certainly feel free to go back and watch it over again. Then on a positive note, for those of you that are here in the room, Kathy just snuck to the back of the room with some popcorn for all of us, but you can't have it in here, so as we exit, feel free to grab some popcorn and enjoy lunch. So thank you.